If you've ever trained on clicks and got a worse ranker, position bias is usually why. We'll debias click logs and build better learning signals you can actually trust. Many teams train on clicks because clicks are cheap and plentiful. The problem is clicks are tangled with where results appear. A popular result gets more clicks because people see it first, not because it is always better. By the end, you will understand a simple debiasing pipeline and how to turn raw clicks into training signals that improve learning to rank models without needing massive infrastructure. I'm Professor Pi, teaching search and IR from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Position bias shows up as an ugly feedback loop in real systems. You surface one set of documents, people click them, you treat clicks as truth, and then your model doubles down on those same documents. Success means breaking that loop so your model learns relevance instead of popularity. The practical trade-off is noise versus bias. Click corrections reduce bias, but can increase variance. That is manageable if you clip extreme corrections and use self-normalization. Intuitively, we want to give a click at rank 5 more credit than a click at rank 1 because fewer people examine rank 5. Imagine 3 short queries where a document at rank 1 gets clicks every time, while a good document at rank 5 gets 1 click out of 10 impressions. Naive rates favor rank 1. Debiasing reweights clicks by estimated examination likelihood, so deep clicks punch above their weight. We will build a tiny click log, estimate position propensities, compute inverse propensity scoring, stabilize with clipping, and do one step of learning to rank to see if debiased signals help. Now we'll construct the toy click log and look at naive CTRs. This snippet constructs a toy click log and computes naive document CTRs. The list clicks holds tuples of query, doc, rank position, and a binary click, giving us a compact, inspectable dataset. We count clicks per doc with CLK and impressions with IMP, both built using simple counter comprehensions. The ratio clock D over IMP D is the naive CTR that ignores position bias. We sort documents by this rate to produce a naive ranking and print the rates for quick inspection. The printed CTRs show how raw clicks can tie or mislead before correcting for position. Next, we'll estimate how likely each rank gets examined and form inverse propensity weights. This snippet estimates position propensities and inverse propensity weights. We aggregate clicks and impressions by position using pause_click and pause_imp, which provide p-click position as prop. The dictionary W stores inverse propensities, which are the core correction factors used by position-based debiasing like PBM and IPS. Intuitively, a click at a low propensity position gets more credit because it was less likely to be examined. We print each position's propensity and its inverse to make the correction strength explicit. The result shows strong bias toward rank 1, motivating the need for now we'll apply inverse propensity scoring and normalize to reduce bias. This snippet computes self-normalized IPS document scores to debias clicks. The dictionaries SN and SD accumulate weighted clicks and weighted impressions per document using the inverse propensities W. We form IPS as SND, the SNIPS estimator, which reduces bias compared with raw CTR by normalizing the credited clicks. Sorting IPS yields a debiased ranking that better reflects relevance rather than position. Compared to the naive CTRs, these values break ties and downweight top-ranked exposures. The printed ranking reveals which documents remain strong after position correction. Next, we'll stabilize the estimator by clipping extreme inverse weights to control variance. This snippet clips large weights to reduce IPS variance and stabilizes scores. We cap inverse propensities with clip to control how much a single low position click can influence estimates. Using W-clip, we recompute self-normalized scores, IPSC, by accumulating weighted clicks and weighted exposures in ACAC. Clipping trades a bit of bias for a sizable variance reduction, which improves training stability and reproducibility. Increasing clip gives more credit to deep clicks, but can be noisy. Decreasing it is safer but less sensitive. The printed values are smoother, yet preserve the debiased rank. Finally, we'll take those stabilized debiased signals and do a single learning to rank update and evaluate with nDCG. This snippet performs a one-step LTR update and evaluates with nDCG. The dictionary S holds a base score per document, representing a static retriever like BM25. We form R0 from S, then R1 from a convex update that moves scores toward the debiased signal, IPSC, with learning rate 0.7. The DCG lambda computes discounted gain using IPS-C as pseudo-gains, and Z normalizes to nDCG. Increasing the learning rate makes the update more aggressive, but can overshoot. Decreasing it is more conservative. The printed nDCG shows whether the debiased update improves ranking quality. Recap. What it is: a simple pipeline that turns raw clicks into inverse propensity-weighted pseudo-labels using self-normalized IPS and clipping. When to use it: whenever clicks are your training signal and position bias is a real concern in production or offline evaluation. One caveat: debiasing lowers systematic bias, but can raise variance, so stability measures like clipping and small learning rates matter. Next step: tune the clipping threshold and the learning rate while measuring nDCG on a larger held-out set to find a practical bias variance sweet spot. If short practical IR helps you, subscribe and watch the rest of the Learning to Rank and evaluation videos.